Hi, this is John Ainsley, CTO at Doulos. Easier UVM, Parameterized Interfaces. This video is a tutorial on using parameterized interfaces in System Verilog and in UVM. So what's the issue with parameterized interfaces? Well, one of the issues is that in System Verilog, ranges can only use constants and parameters. So if we need any kind of parameterized range within a System Verilog interface or module, then the expressions that make up that range have to be based on parameters, not on variables. So we're really bound to make use of System Verilog parameters if we want to create parameterized module-based code. So let's suppose we have a System Verilog interface that contains one or more parameters. Outside of that interface, we may want to create ranges where the range depends on the value of the parameter in the interface. And there we immediately start hitting tool issues and language issues. For example, suppose we have an instantiation of the parameterized interface, and we then want to create a vector whose size goes from n-1 down to 0. Well, the System Verilog LRM allows us to create a range such as if1.n-1 down to 0. But would immediately hit tool issues. Some System Verilog simulators will allow us to compile this code, others won't. We may also want to access parameters used in interfaces from our class-based verification environments. And there we hit an even more severe issue, which is that in System Verilog it's simply illegal to write hierarchical name references within classes within packages. You just can't do it. So we really need a better solution. Well, fortunately, there is a solution that kind of works in all circumstances, and that's to place any common shared parameters into System Verilog packages. So here we have a parameter w in a package constants package, and parameters in packages can be used anywhere in the System Verilog code. They can be used in interfaces, in modules, or in other packages. So now what we've done is to put our single shared parameter value in a package, and we can use the System Verilog import keywords to import the contents of that package, including the parameters, wherever we want it. So in a module, we've imported the parameter w and used that in defining the range of a vector. We've also used the parameter w to set the parameter n of the interface as we instantiate the interface. We can also import that same parameter w into a package and use it in our class-based verification environment. So in a sense we've solved the problem. We've got some System Verilog code here that's standard, that's portable, that's supported by all the simulators and synthesis tools. The trouble is it's not really what we want because it creates some very nasty dependencies between the various chunks of System Verilog code. In particular, each of our modules and packages and interfaces now potentially needs to know about our constants package. We need to agree on the names of the constants and make sure that we use the same constants from the same package everywhere in our System Verilog code. And of course, if we're trying to reuse existing IP, that's just no good as a solution. We really want a solution where we can take existing IP written by different people in different places and then parameterize it all in a uniform way. So this is a kind of fallback solution. In any situation in System Verilog, you can always access parameters that have been placed in a shared package. It's a fallback solution that always works, but it's really not the solution that we want if we're interested in reuse. So let's move towards something better and take a look at UVM. When you try to access parameterized interfaces from a UVM verification environment, you immediately hit other different problems. So suppose we have our same parameterized interface with a single parameter, and we try to access the contents of that interface from our UVM verification environment using a virtual interface, which is the obvious way of doing it. So here within a UVM component, we have a virtual interface VIF. We're getting the value of the virtual interface through the configuration database, and we can then attempt to access the contents of our parameterized interface through the virtual interface. Well, so far so good, but it all breaks down when we try and actually set the virtual interface into the configuration database. And the reason for that is in System Verilog, whenever you instantiate an interface, in effect you create a new data type. Now, interface instances and virtual interfaces are not literally data types in System Verilog, but in effect they behave as data types. So if you want a virtual interface to refer to a distinct parameterization of a System Verilog interface, effectively you need a virtual interface of a different data type. So when we try and set the value of our virtual interface into the configuration database, we're actually going to get a compile time error because we've got, in effect, two mutually incompatible data types here. The call UVM config db virtual if set is effectively using the type virtual if with n set to 0, the default value of the parameter, whereas our actual interface instance if1 in effect has the type virtual if with n set to 2. So two different data types, they're incompatible, we can't do it. Well, we can apply some band-aids to fix this problem by changing the type of the virtual interface within our UVM verification environment. So now we've consistently used the same virtual interface type everywhere, virtual if pound with n set to 2. So that will now compile and simulate OK, but it's definitely going in the wrong direction because our UVM component now depends on a specific instantiation of our System Verilog interface. This UVM component only works where we've instantiated our interface with the parameter n set to 2. Any other value of the parameter and it just won't work. Although we now have something that we can compile and simulate, it's definitely not the solution that we want to our problem. So let's move toward a better solution. What we've looked at so far is the usual way of providing communication between a UVM verification environment and the module-based world in System Verilog. The usual way is to make use of virtual interfaces. So a top-level module in UVM can set a virtual interface into the configuration database. Individual agents can then get that same virtual interface from the configuration database and set the virtual interfaces within their monitors and drivers to point to the actual interface of the design under test. That works, that's the way many people use UVM, but it does suffer from this fatal flaw when it comes to parameterized interfaces. When it comes to dealing with parameterized interfaces, there is a better solution. The better solution doesn't make use of virtual interfaces. Instead, it makes use of references to objects, where those objects have a type that's a class, where the class is actually defined within the scope of the System Verilog interface. So in this approach, we replace our virtual interfaces with references to some abstract base class. We then create a concrete implementation of that abstract base class that actually implements the methods that we're going to use to access the pins of the DUT within the System Verilog interface. We then create the declaration of that class within the scope of the System Verilog interface. So within our interface we have a class that can implement methods such as read and write, and because those methods are textually written within the interface, they have access to all the variables and wires, and for that matter parameters, of the System Verilog interface. We then create an object of that concrete class, and the object we can instantiate within our UVM verification environment. That object can be a UVM component, so we have all the benefits of UVM in writing and instantiating that object. The virtual interfaces are then replaced by references that ultimately are references to that concrete object. And the concrete object is of a class which is actually defined not as part of the UVM verification environment, but as part of our System Verilog interface. So there's a very cunning System Verilog trick going on here, that we have an object within the object-oriented world, within our UVM verification environment, and the class of that object, the type of that object, is actually defined not within the UVM verification environment at all, it's actually defined within the module-based world. And because the class is defined within the System Verilog interface, the class can actually access all of the variables in the System Verilog interface. By the way, credit for this approach should really go to Dave Rich, Jonathan Bromley and Gunter Klassen. These guys have been trying to popularise this approach for a number of years now. All the work that you see presented in this tutorial was originally inspired by their work, although I've added a few new twists to it. So let's take a look now at the code. We'll start off with the abstract base class. Now, those of you who already know some System Verilog and are sharp-eyed may notice that this isn't actually an abstract base class. We could have used literally an abstract base class that only contains pure virtual tasks. There's one and only one reason why I'm not literally using an abstract base class here, and that's because I ran into certain tool issues with some of the System Verilog simulators. So if your System Verilog simulator allows you to use abstract base classes in this situation, fine, you can go ahead and use true abstract base classes. So here we have our pseudo abstract base class, which is a class which in this particular case extends UVM component. You can extend any suitable UVM base class, including UVM object. The only reason that we've used UVM component here is that the instance of this class can now be a component within the UVM component hierarchy, so we could use the configuration database to pass information down and parameterize this particular component. But using the configuration database to parameterize this component is not actually a core part of the technique that I'm showing here. It's just an aside that we've chosen to use a UVM component. Then within this class we write whatever methods we need to access the variables and wires within the interface. For example, we could add methods to return specific parameter values if that's what we wanted to do. So if we'd got some parameterized bus widths within our System Verilog interface, we could have methods here to return the bus widths. What we've actually got is a pair of write and read methods, which is something you might reasonably expect to write and read the variables in the interface. This class is not parameterized as such. This is an abstract base class that we're going to use to access all the various instantiations of our parameterized System Verilog interface. So it's very important that any ranges within these methods exceed the maximum parameterized values of our actual parameterized System Verilog interface. So we've chosen to make the arguments here long ints, so we've got at least 64 bits to play with. You just need to make sure that the values here are big enough to deal with any of the interesting parameterizations of your System Verilog interface. So that's our abstract base class. Note that the name of the abstract base class is clock and data interface base, and it's got two methods, write and read. Now let's see how we can use this abstract base class. And I'll show the example of the driver. So here we have a regular UVM driver component. And whereas normal practice within a UVM driver would be to have a virtual interface through which we're going to access the variables in the interface, here we've replaced the virtual interface with a variable whose type is our abstract base class, clock and data interface base. And then within the body of the driver, within the run phase task, we can simply call the write and read methods of that abstract base class. So here you can see the call to mClockandDataInterface.write, passing the address and the data that were picked out of the transaction object. So this is the driver code, and we'd use a very, very similar style within the monitor code. Now let's move up and look at the actual concrete object that's going to be used to access the System Verilog interface, and which this variable mClockandDataIF will end up referring to. So we'll move up to the build phase of the agent. The actual concrete object through which we're going to access the System Verilog interface can be instantiated anywhere within your UVM verification environment. Here we've chosen to instantiate it within the agent, which seems reasonable. So each agent needs to access an interface. We've instantiated the object through which we're going to access that interface in the agent. But you could have instantiated this object at the next level up in the UVM hierarchy or the top level of the UVM hierarchy. So we're instantiating our concrete class object through a factory method call clock and data interface base type ID create. And the actual object that we create won't be of type clock and data interface base. It will be an object of the concrete class that's actually embedded in the interface. And a key part of this whole technique is making sure that you choose the right string name for this object, because that string name is going to be used when doing factory overrides later on to make sure that we actually pick up the right type of concrete object in order to access the particular instantiation of the System Verilog interface that we're interested in. So the strings here have a very specific form. They start off with the interface name, and then we're appending as a suffix the values of all of the particular parameters to that interface, separated by underscores. This is just a convention that we've used in this particular example. So in this particular example, the actual value of this string will be either clock and data IF44 or clock and data IF88, where 44 and 88 represent the values of two parameters to our System Verilog interface. So in the build phase of the agent, we're instantiating our concrete object. Then in the connect phase, we're setting references within the monitor and driver to actually refer to that concrete object that's just been created with the factory method call. Now let's take a look at the parameterized interface itself and the actual parameterized class definition. Without losing any generality, we've got an interface with two parameters, an address width and a data width. We've then used the address width and the data width within the ranges of the address bus and the data bus within the interface, and then nested within the interface such that they have access to the variables within the interface, we have the full definition of the concrete class, clock and data class. And it's critical to this method that this class is parameterized with exactly the same parameters as our System Verilog interface. That way we can make sure that each unique instantiation of the System Verilog interface has a corresponding unique instantiation of our concrete class. Then finally, in the interface, we have a helper function, useConcreteClass. UseConcreteClass is actually going to set up the factory override for us, as we'll see a little later. So now I'm going to expand the declaration of clock and data class. Here we go. So clock and data class is a parameterized class that extends our base class, clock and data interface base. Because it's parameterized, it needs to be registered for factory automation using UVM component param-utils. And then we have the definitions of all the methods we're going to use to access the interface, so the write and read tasks in this particular example. Then after the concrete class comes the definition of the useConcreteClass function. And this function is going to do a factory instance override to replace instances of clock and data interface base, our abstract base class, with instances of the clock and data class parameterized with whatever the appropriate parameter values are. So each time we come to instantiate our interface with a different set of parameter values, we're going to have a different call to useConcreteClass, which will set up a factory instance override unique to that particular instantiation of our concrete class. And we're going to identify the particular instantiation using the string names that I highlighted earlier and that are being assigned to this path name variable. So as I said before, the correct choice of path name is key to making sure that we actually get the correct objects instantiated within our UVM agents. So again, the form of the path name in this factory instance override is star.clock and data if, and then we're appending the values of the parameters, AW and DW in this case. So this instance override is going to apply to precisely the instances of our System Verilog interface with exactly these parameter values and no other instances, provided we set up the right strings when we create those instances. So finally in the code, we can see the calls to make those factory overrides. So before we call run test to actually instantiate the whole UVM verification environment, we're calling useConcreteClass for each of the distinct instances of our System Verilog parameterized interface. So here we've got two instances, one with address width and data width both set to 4, another instance with address width and data width both set to 8. And then we've set useConcreteClass for each of those, and useConcreteClass will create the appropriate factory overrides for that specific instantiation of the parameterized interface. And then all of the code I've shown will just spring into life and it will work. So what we've managed to do here is we've managed to keep the UVM verification environment itself generic, but through that generic UVM verification environment, we've been able to access multiple specific instantiations of the same parameterized System Verilog interface. You can now play with this example yourself using the easier UVM code generator and EDA Playground. So we've set up an example for you at the URL shown here. This is a screenshot of EDA Playground. In the tabs on the left-hand side, you can see all of the control files and code fragments necessary to run the Easier UVM code generator on this example. On the right-hand side, you can see a dummy module instance, and at the bottom of the screen, you can see a transcript showing the simulation output when the example actually runs. So if you type in this URL and hit the Run button, then you'll be able to run this example for yourself. If you actually want to be able to see the full expanded UVM verification environment so you can see exactly what's going on, then before you hit the Run button, make sure you check the box Download Files After Run. That way, when you hit Run, then first of all the Easier UVM code generator will run to generate the full set of UVM code, then the chosen simulator will run, and then the code will get downloaded so that you can run it locally. So I encourage you to have a go at this yourself and enjoy. So at Doulos we deliver training classes worldwide in any of the subjects that you can see in this slide, obviously including System Verilog and UVM. You can find out more about any of these training classes from our website, www.doulos.com.